This is Mark Aurelio will talk after me, well, I won't go through his kind of outline. He'll talk you through that, but there's going to be, at the end, there's going to be another 10 to 15 minute sort of Q&A period when both of us will come up together, so you can ask questions about any part of the presentation up till then. Okay, so first of all, at a very general level, where do we locate unsupervised learning within machine learning, within artificial intelligence and deep learning and so forth? People often talk about kind of three different types of learning: supervised learning, unsupervised learning, and reinforcement learning. And I find this categorization slightly unhelpful. I think it's better to think along two dimensions of variability here. So one of them is active versus passive. So in the supervised or in the unsupervised setting, the learner, the agent, if you want, is passive. It's just receiving data. It's not acting in any way so as to modify the observations of the data that it's going to receive in the future. And then we have the active setting where we have what we would normally think of as an agent that actually interacts with an environment and thereby influences the information that it's going to receive and the state that it's going to be in. And the other kind of degree of freedom here is whether or not there's a signal coming from a teacher. So obviously, in supervised learning, you've got targets, you've got predefined training targets that have been given to you by presumably a human teacher. Unsupervised learning, you take those targets away and you're just learning directly from the data. And so the analog in reinforcement learning would be, well, normal reinforcement learning with extrinsic reward. You have a teacher. When you take the teacher away, you're in this setting of what we call intrinsic motivation or exploration, where you're just finding something out about the environment in some sense for the sake of finding it out, rather than for optimizing a particular reward. And it should make it clear that neither of these categorizations are hard and fast. There's kind of a continuum between having a teacher and not having a teacher. There are varying degrees of supervision. You can have semi-supervised learning. You can have very sparse extrinsic rewards coupled with intrinsic rewards in reinforcement learning. There's also a kind of continuum between active and passive. So there's a fully active reinforcement learning agent at one extreme, and then there's something like active learning where you have what is essentially supervised learning, except that you're making a decision about what kind of data to look at yet. And curriculum learning is another example of that. So anyway, this talk will mostly be focused on the unsupervised learning setting. But I will also try to talk a little bit about intrinsic motivation and reinforcement learning without a teacher signal. And hopefully I can get across the idea that all of the stuff we're talking about here should be relevant to both settings. So we're really talking about learning without a teacher in general, rather than specifically learning for what's usually thought of as unsupervised learning or for unsupervised reinforcement learning. Anyway, so following that preamble, the first question is, so if what we want to do here is talk about how to learn without a teacher, maybe the first question is, why would you want to do that? So if your ultimate goal is to create intelligent systems that can perform a wide variety of tasks, so whether these are reinforcement learning active tasks or supervised tasks, you might ask, well, why don't we just teach them how to do those tasks directly? Gather lots of data and teach them how to do it. Well, the first sort of complaint that everyone brings up here is, well, it can be difficult to obtain all of this kind of training signal, all of this teaching signal. So in the case of supervised learning, you have to get huge quantities of labeled data, which can be difficult to obtain. In the reinforcement learning case, the active case is a little bit more subtle than that. The reward signals are generally defined in a more programmatic way. They're not kind of hand assigned to specific observations. But they're still difficult to define. Someone still has to think about what the task should be and what the reward structure would be. And so anyone who's worked in reinforcement learning knows that determining the reward structure is really a big part of the problem. That's where a lot of the work goes. Well, the second point here is a little bit more fuzzy. It's a somewhat subjective point. But I think there's a general consensus that unsupervised learning feels a little bit more like the way a human learns, right? Babies are, to some extent, we teach our children things, we tell them things, but for the most part, they explore and interact with the world and find things out about the world without being told how to do it. And so there's just a general feeling that if all we're doing is giving our agents signals and asking them to exactly optimize or match those signals, they're never really learning in a way that we think of as human intelligence. But I think the last point is the really critical one, which is that we don't just want to solve a particular set of tasks. We want to rapidly generalize to new tasks and situations. And this is, evident already in the supervised learning setting, but it's much more evident in the reinforcement setting. So it's, there's no way we can hope to build a kind of generally intelligent agent by exposing it to all of the possible scenarios that it will ever encounter in its lifetime. The world doesn't work like that. Things change, novel situations arise. The key element of general intelligence, I think, is actually not the ability to learn lots of things, but rather the ability to rapidly adapt to new things and new situations. And I think this is something that there's a general feeling that this is just not happening with supervised learning or extrinsic rewards. And so I say it's not happening. Of course, there is this, there's a whole field of, transfer learning, right? Teach on one task and transfer to another. So multitask learning, one-shot learning, these sorts of things. And without meaning any disrespect to people working in this field, I think it's fair to say that it does kind of work. So, an example that I remember hearing about not long ago is that, for speech recognition systems, and this is for, commercial speech recognition systems as they're used at Google and places like that, when you've got a language for which you don't have very much data, you can sometimes kind of bootstrap from another language that's quite similar, and you do have a lot of data. So you're getting an actual sort of practical, commercial improvement by transferring from a similar task. But you're not transferring very far, typically. You're going from, maybe one dialect of one language, one closely related language to another. And in general, there's a sort of gut feeling that this kind of transfer doesn't seem to go, it never generalizes as far or as fast as we want it to. And one kind of hypothesis for this is that there just isn't enough information in the targets and the rewards that teachers can provide for these agents for them to be able to learn transferable skills. And so I highlight this word skills. I saw a talk recently by Satinder Singh, and he said something that really stuck in my mind, which is we need to stop thinking about teaching agents to learn tasks and start teaching them to learn skills. People don't solve a series of tasks in isolation and then transfer them. Rather, we pick up skills through our life that we're able to reuse and flexibly adapt later on in life. Okay, so a lot of you have probably read this quote before from Yann LeCun. He says, if intelligence was a cake, unsupervised learning would be the cake, supervised learning would be the icing on the cake, and reinforcement learning would be the cherry on the cake. And some of you might be a little bit surprised to see someone from DeepMind quoting this, but I don't read it as a slight towards reinforcement learning, but rather a statement of this massive disparity in the kind of volume of information between these different types of signals. So it's very clear that the targets for supervised learning have a lot less information than the input data. And I'm actually going to go through a specific example of that in the next slide, just to kind of make that point very clear. But of course, reward signals for reinforcement learning contain even less. So you might have a very long sequence of actions, interactions with a complicated environment involving vision, sound, whatever, and then at the end you're just going to get a single bit of reward. You either succeeded or you didn't, a 1 or a 0. And it's kind of amazing that agents can learn at all under those circumstances, that given so little kind of information to latch onto, they can do something. But it's also clear that if we turn this around, if we stop thinking about signals from teachers and start thinking about the signal that's just inherently present in the data, then we've got this basically unlimited supply of information about the world. We can just go and trawl the whole internet. We can set a digital camera running. We can gather limitless amounts of information if we don't have to worry about how we are labeling or assigning reward to that information. It just seems obvious that we should exploit that. And so just to go through a little example here, and this is a little bit pedantic in some sense, but I think it's a good point to make. So let's say we look at ImageNet and we look at the training set. It's got around 1.28 million images, and each one is assigned one of 1,000 labels. I think I've got these numbers right, but it's not really important if they're wrong. If those labels are roughly equally probable, there's an equal distribution across classes, then basically the set of labels contains something like, well, log of 1,000 times 1.28 million. So 12.8 megabits of information. And when you think about it, that's not really that much. People are often surprised that with beginners, when people sort of start working on machine learning, they're surprised that their neural networks can overfit on such a big data set. But the point is that if you're doing supervised learning, you're not overfitting on the inputs in the data, you're overfitting on the targets, and there aren't actually that many targets. So by contrast, if you were to take the whole set of the images uncompressed at 128 by 128 resolution, you'd be looking at by my rough estimate, something like 500 gigabits of data, so 4 orders or more of magnitude more. And so there was this recent paper that showed, well, these neural nets are in some sense have too much capacity, right? We can take ImageNet and randomize the labelings, and it can still solve the training set perfectly, which means that what it's learning is gibberish, right? It's just memorizing a bunch of labels that have no relationship whatsoever to the inputs. And actually, that's not that surprising, right? The convolution net has maybe 30 million weights, and you're asking it to learn 12.8 million bits, right? So you do the math. You don't have to embed that many, less than 1 bit per parameter, less than 1 bit per weight, right? It's not that difficult for it to do. But of course, that same network wouldn't be able to memorize the pixels. If we randomize the pixels and asked it to do density modeling, asked it to model the pixels, it just wouldn't work at all. And so actually, the best unsupervised, or the biggest unsupervised models for ImageNet, I'm told, are now starting to overfit at 32 by 32 resolution on the training set, but they're not memorizing it, they're just overfitting somewhat. Anyway, this is just to sort of keep this in mind in terms of like the orders of magnitude, the degrees of disparity between the amounts of information that are available in data versus training signals or labels. Okay, so one slide, what is supervised learning in one slide? Well, it's really pretty straightforward, honestly. You have a data set of inputs X, and you label them with targets Y, and your task is predict Y given X. And typically, you're just doing this with maximum likelihood. So you have a loss function that is the sum over these XY pairs in the data set of the negative log probability of the targets given the inputs. And this is really, really this is still the engine that's powering an awful lot of deep learning, right? A lot of the headline results, going back to sort of the ImageNet classification results and the speech recognition results and machine translation and things like that, they're mostly, so obviously there's a lot more to it than that. There's the architecture of the network, there's the way you optimize the network and things like that. But in terms of the actual loss function that you're running, it's very simple. It's an ancient statistical technique. So then the question is, well, what happens when we take the targets away? So now our data set just consists of a lot of X's and no Y's. What's the loss? What should the loss be? And of course, this is the fundamental challenge of unsupervised learning, right? The task is undefined. By definition, we don't have a task anymore. And that's exactly what makes unsupervised learning hard, but it's also what makes it interesting, because we're not just optimizing some predefined task, so we have to kind of come up with something that somehow indirectly gives us what we think we want from the system. And the problem is that even if we do that, so let's say we could say in vague terms, well, what we really want from this thing is a single task that would allow the network to generalize to many other tasks. So you want to learn whatever it is that will allow you to rapidly generalize to whatever life is going to throw at you in the future. But then the question is, well, which tasks are you talking about, right? If you predefine a set of tasks, then actually you're just doing supervised learning or reinforcement learning again. You're just doing it at one step removed. You're kind of saying, optimize this thing so as to get the best possible score on that thing, that set of tasks. And I'm not convinced that that will ever give us this kind of generalization we want either, because it really has to be able to generalize to something that you didn't predict at the time when you made the model. Okay, well, the simplest thing you can do, arguably, is just basically do the same thing as you were doing before, only without the target. So now you're doing maximum likelihood on the data instead of the target. So this is just good old-fashioned density modeling. And what's the goal of density modeling? Well, fundamentally, what you're trying to do is learn the true distribution from which the data was drawn. And I've got true in kind of scare quotes here because there's always this question of, well, all you actually have is a data set. Is it really meaningful to talk about a true distribution, or should you just try to learn that data set as well as possible? And there's an endless sort of philosophical rabbit hole that I don't want to get into there. But the basic idea is you're training the system to try to learn as much as it can about the data. Learn everything. Every pattern, every regularity you find in the data should in some way allow you to reduce this log loss, right? To improve these log probabilities. Well, I think before we even get into any of the details of that, we should, so, and before I go any further, I think one thing that I want everyone to take away from this tutorial is that there are no clear answers about how to do unsupervised learning, right? As I said, that's what makes it difficult, but also makes it interesting. And you're going to hear a lot of different models and different approaches already from me and Mark Aurelio, and you'd hear a lot more if you kind of polled people in the field in general. So there really isn't a consensus on what the best thing to do is. But one thing that you'll often hear is that, well, we shouldn't try to understand everything at once. That doesn't make sense. We should focus on things that we have some idea or some belief that will one day be useful for us. And I was reading this book, A Death in the Family by Karl Ove Knausgård, I think you pronounce it. And I won't read out the quote. It's kind of long. You can look through it. But the basic idea was the narrator was walking through the streets of Stockholm, and he sees this, very striking cloud formation. I think maybe it's a sunset or something like that, and the clouds are colored and they're beautiful. And he looks up, and he realizes that no one else is looking at the clouds, and he wonders, why does no one else pay any attention to this? This is some, beautiful, intricate pattern that you're never going to see again in your life, and yet no one's looking at it. And obviously, the reason is we're not looking at it because we don't need to, right? Other than maybe gauging, whether or not it's likely to rain or something like that. We don't really need to look at the clouds. They're an inexhaustible store of structure in some sense, of patterns, of information, but they're not patterns. We can pretty safely say they're not patterns that are going to be useful for us, unless maybe you're a professional meteorologist. And so that's a kind of ongoing conundrum here, is given that you can't really hope to learn everything, shouldn't you be a little bit more focused about what it is that you're trying to learn? Okay, and actually I'm going to kind of repeat that again on this slide. When you say, oh, let's do unsupervised learning just by density modeling, let's just model everything. Well, one thing is kind of obvious is density modeling is hard. So you go from one extreme to another. You didn't have, back in the reinforcement learning supervised setting, you didn't have enough bits to learn from. Now you end up with too many, just in terms of, if you're talking about, high definition video running at 60 or whatever it is, 30 frames a second, there's too much information flowing into the system. Even with today's computers, it's very difficult to model all of that at once. And the second problem, to which I would argue that we have a little bit more of a solution, is you have to deal with complex interactions between these variables. There's a kind of curse of dimensionality. These are very high dimensional, very complex, and difficult to model data. The second problem is actually more fundamental, and it's basically a restatement of what I just said in the last slide. It's something you'll often hear people say, not all bits are created equal. This is a discussion I hear over and over again among my colleagues. Basically, the log likelihoods, if all you're doing is optimizing log likelihoods, they depend much more on these really kind of low-level, insignificant details. Things like exact correlations between neighboring pixels, word-level n-grams, where n might only be the last 2 or 3 words, but getting those statistics very, very precise. And those aren't really the things that we want to learn about intuitively, right? Rather, we want to learn about high-level structure. We want to know what are the contents of the image. Was it a cat or a dog, rather than precisely what value of color each pixel was likely to be. We want to know about the semantics of the language, rather than precise transition probabilities between n-grams. And there's another problem, which is a more general problem, a problem for unsupervised learning, and more broadly, which is even if you do have, in some sense, the right loss function and it gives you the right underlying structure, it's not always clear how to access that underlying structure for future tasks. And this is really where the issue of representation learning comes in. So, in order to solve these kinds of problems, neural networks have to learn interesting and essentially what should be useful representations, but they tend to be kind of black boxes, and it's difficult to access those representations. And I'll come back to this later in the talk. Okay, so one nice thing about densities is that you kind of get a generative model for free. So if you've learned how to model the data, this probability distribution of the data, as long as you can draw samples from that distribution, then you have, by definition, a generative model. And generative models are nice in a lot of ways. I think, fundamentally for me, the most important thing is that they allow you to see what the model has and hasn't learned, right? You can generate from the distribution. So log probabilities, metrics of any sort will only tell you so much about how good your model is. When you generate from it, then that's when you see what kinds of patterns it has actually learned and what kinds of structure it has actually managed to embed. And so this is kind of like a quantification of Richard Feynman's famous quote, what I cannot create, I do not understand. So we're going down this path of, we're building creative models that have to be able to actually create the data to prove that they've understood it. And another use for these things is, if you've got a generative model, you can use it, for example, to imagine possible scenarios. And that's been something that people have explored in the context of model-based RL. But I'm not going to talk further about that just now. Okay, so then the question is, if you're on board that doing density modeling is a good idea, and that's a big if already, then the next question is, well, what models should we use to do density modeling? And what I'm going to talk about now is autoregressive models, which are a very simple, very powerful class of models that I think do a very good job of modeling a surprisingly wide range of data types. Okay, so the one piece of math, which is probably, I'm sure it's familiar to you all already. Basically the only piece of math you need to know for autoregressive models is the chain rule for probability. So essentially, given any joint probability over a bunch of variables, you can always decompose it as a chain of conditional probabilities over all the variables so far. And what's important here, so in this case, here we have a language model, so we have the cat sat on the mat. You start off with probability of the, then you have the probability of cat given the, probability of sat given the cat, and so on. And there's a very natural ordering here. But actually, the chain rule still works in whatever order you want. So you could scramble this ordering and run the same thing in principle. In practice, and this is something I'll discuss a bit further on, the ordering you choose is very important for, that is critical to how well you're actually going to be able to learn the system. It introduces a kind of inductive bias. And that's a whole, there's a lot of debate around that for autoregressive models. Actually, like a short aside here, I once trained a character level neural network language model where I allowed it to choose which character to predict next. So rather than just going from right to left, left to right like usual, it could choose where to look. And what was interesting is that rather than doing, it almost did the characters in the normal order, except that it would skip over the first letter of every word and go straight to the second one, then get to the end of the word and go back to the first letter. And my kind of guess for why it did that is that in English, the second letter is often a vowel, which means it has lower entropy than the first letter. And so I think if there's a sort of fundamental rule for how we should order auto-associative predictions, it's probably that the system always wants to take the safest bet first. It wants to make the prediction that it's surest of, given the information so far first, and then move on to the next one. But typically, that's roughly what you get. If you have a time series and you make the predictions in order of time, that's roughly what you're getting. So anyway, autoregressive network, well, it's just basically, applying that trick to a neural network. So you take high-dimensional data and you split it up into a sequence of small pieces where you have to choose what the sequence is, and you predict each piece from those before. And to me, this basically answers, and now Mark Aurelio might disagree with me on this one. We had a long debate about the relative merits of autoregressive models, so you'll hear more about that later. But I think that this kind of answers the curse of dimensionality part of the problem. Because you're only predicting a small piece of the system at once, you no longer have this issue where you just can't handle the covariance or the interactions between many variables at once. And the conditioning on the past, so this probability has been split up for you into a chain, a sequence of independent predictions, each of which is conditioned on the past state. This is done via the state of the neural network. And so this tutorial isn't going to talk very much about, in fact, hardly going to talk at all about deep learning architectures. It's much more about loss functions and training methods. But when it comes to autoregressive networks, there's probably like three basic structures have emerged as the winners. There's gated recurrent neural networks like LSTM and GRU. There's masked convolutions where the masks are there to ensure that the future state is not accessible to the past state when it's making predictions. And recently, there's been a growing trend towards transformers where this, convolutional or recursive state is removed completely, and conditioning on the past is done entirely through attention mechanisms. Anyway, whatever you choose, you end up with the same loss function and broadly similar behavior. And then you haven't, given this network that embeds the past as some sort of high-dimensional vector, you then pass that through the output layer of the network, whose job is essentially to parameterize the prediction. So whatever your predictive distribution is for what comes next, and most often it's a softmax as a classification, then your output layer is just giving you the parameters of that prediction. Okay, so just to see how that works for a recurrent neural network language model, which is maybe one of the oldest sort of neural language models, and that we had Jeffrey Ellman doing this back in the early 90s, finding structure in time and so forth. The system has this recurrent connection. It takes in vectors of input at each step and cyclically kind of feeds those in along with its own state from the previous step to build up a state that represents the history at any point in time, and then it makes predictions based on that. Okay, so why do I like autoregressive models so much? Well, one point which I think is already clear is they're quite simple, right? Once you've picked an ordering, everything, you just sort of turn the handle, right? The loss function is just done for you and you don't have to think about it. And it's all normalized, and you don't have to worry about having properly defined probability distributions and things like that. And a kind of related point there is it's very easy to generate samples. So basically, how do you generate samples from an RNN, from an autoregressive model? You just pick a sample from the predictive distribution at each step, and then feed that in as if it's the input at the next step. So I always think of this as sort of like the equivalent of dreaming for a neural network for a computer. When we dream, we're imagining things that might happen and then kind of treating them as if they actually have happened. But really, the main reason to use autoregressive models is less poetic than that. It's just that they give the best log likelihoods for lots of types of data. And in particular, the kinds of data that I think we're most focused on when it comes to general intelligence, things like images, audio, video, text. These are something like the four senses of the digital world, right? These are the things that you find on the internet and that you find in huge amounts digitized. But of course, there are disadvantages of these types of models. And the first one is just that they're very expensive. As the data, basically, you have as many predictions as you have pieces in the data. And so if you're splitting your high-dimensional video, your high-density video up into individual pixels or individual color channels, you're talking about millions of predictions per second. And even with today's computers, that becomes extremely expensive. And you can mitigate this to some extent by parallelizing things during training, but that doesn't work during generating, because during generating, it has to be serial. You have to pick something from the predictive distribution and then feed it in and then pick something again. There's this issue of order dependence. So as I said, it really does matter what order you make the predictions in. And a kind of a thing that follows on from that is that you can't easily impute missing data out of order. I think Mark Aurelio is going to talk a little bit about that. So by impute, I mean, for example, given a sentence and some missing words, fill in the missing words. Autoregressive models are kind of good at filling in possible futures or guessing possible futures, but not at filling in some part of the past. Now, in principle, you could do something like a beam search and try to infer what those words must be, even with an autoregressive model, but it's very awkward. Another issue that a lot of people worry about with autoregressive models is this idea of teacher forcing. So basically, because the system is only ever being trained to predict one step ahead, it's never learning how to generate many steps ahead. And I think this is usually counted as a demerit for autoregressive models in the context of generative modeling. And people say, oh, they can't generate long sequences. My experience is that modern autoregressive neural nets actually can generate very convincing long sequences. In either case, that's not really the issue. From the context of unsupervised learning, that's not the issue. The worry here would be more that by only predicting one step ahead, they're learning a kind of myopic representation. We're back to this bits not being equal. They're focusing on just the next bit, the next prediction, and not on the large-scale structure of the data, which is what you really want. Okay, so just a quick rundown of why where language modeling is at. Where autoregressive models are at in terms of data. And so for language modeling, I think it's clear they really dominate. In some sense, language models have always been autoregressive. It's just a very natural thing to do here, is to predict the next word given the previous ones. This slide sort of shows, just how advanced it's become. I mean, if you look at these results, you can see there's perplexities becoming, if you know anything about perplexities and numbers, they're becoming ridiculously low with these giant neural network models. As a generative model, they're also getting pretty impressive. So half of these quotes are generated and half of them are not, and they're color-coded according to which is which. If you have a look at them and try and decide which color is true and which color is fake, honestly, I had to ask Oriol Vignals, who gave me this slide, which was which. But it is, in fact, the red ones are fake and the green ones are real. Okay, so a lot of you probably heard about WaveNets. WaveNet it's a slightly different setting here. It's not purely unsupervised. You've got a conditioning signal, right? You've got a text signal, and from that text signal, you generate the data, but mostly it is unsupervised. So even if you run WaveNet without the text, it already generates very convincing audio. It generates a kind of babble that contains real words and even individual phrases. And to me, I was amazed when I saw WaveNet working just because of the sheer volume of data that it has to generate, the frequency of the data. So it's, 16,000 predictions per second, 16 kilohertz to generate sort of raw audio. And a network can do this, and it can remain coherent over long spans of time. And it's now, I think it's pretty clear that this is the state of the art as far as audio generation goes. So pixel RNNs, now this is an interesting one, which is what happens when you take the autoregressive models and apply them to images. Well, here the ordering problem really becomes an issue, right? Like you want to predict all the pixels in the image, but you have to give a specific order that they should be in. And so in speech, anything temporal, there's a clear ordering, right? You predict each audio signal predicated on the last one. There's a temporal order. In pixel RNN, it's pretty much random, right? Or not random, but arbitrary, right? You just have to pick some ordering, and so there's this kind of raster scan ordering is often used, where pixel xi here is conditioned, is conditioned on all the other pixels that have been uncovered so far. And another important, sort of surprising and important thing about pixel RNN, that's actually true of WaveNet as well, is that even though it's modeling what is essentially continuous data, although it's discretized continuous data, it's doing so with a softmax output layer. So it's treating it's actually, I should be more specific here, what it actually models are the individual color channels in each pixel, so the individual RGB numbers in each pixel. So there's 3 predictions for every pixel, each conditioned on the previous ones, like blue is conditioned on red and green and so on. And it's treating those numbers, which are a number between 0 and 255, as if they're just 256 completely distinct classes, which seems at first sight a bizarre thing to do because it throws away this information we have, namely that numbers that are close to each other correspond to colors that are similar to one another. 128 is closer to 129 as a color channel than it is to 255. But somehow just ignoring that and training it as if they're separate classes works better than treating it as if it's continuous. And so you can run this kind of model with a mixture model instead of a softmax, but it works better with a softmax. Anyway. It gives samples trained on ImageNet, the original pixel RNN, and these are all, like in terms of image generation, these are 2 years old, they're very dated. And I'll show you some better images in a second, but it gives textures and sort of like you can see something of the flavor of these real images, but there's local structure, not global structure, basically. So at first sight, they appear to be confirming what everyone said about autoregressive models, although they don't capture global structure. Interestingly, when you start conditioning them on the labels given in the data, then immediately you get much more global structure. And this isn't a specific thing of pixel RNN. This is true of generative models in general. And it comes back again to this issue of bits not being equal. So it seems weird at first. You're conditioning on something that is only, at best, log 1,000 bits. And suddenly your image looks so much better. But of course, the log likelihood isn't going to get much better than log 1,000 bits, right? There's only so much, the information in is the information out. So the log likelihood doesn't change much. The generation, the thing that seems like what we care about, the high-level structure, changes a lot. And this is often used as an argument against density modeling. Okay, but we can go further than that and say, well, what happens if so we've said there's this ordering is arbitrary, this raster scan ordering. What happens if we change it around, right? We were free to do these any way we want. So there's a recent paper, very recent paper, on what are called subsample pixel networks, where the basic idea is to take this autoregressive image generator and change the order of the autoregressive prediction. So it's now, you have this image is sliced up into kind of smaller, like say if it's 128 by 120 image, you cut it up into 4 32 by 32 slices, you model each slice autoregressively, and then you model the next slice conditioned on the previous one, and so on. And there are other tricks going on in here as well. It's not just about reordering. For example, the actual bits within each channel are also reordered so that the lower 5 bits are predicted first, and then the kind of high frequency bits are predicted at the end. So there's a lot of clever kind of restructuring going on, and there's a real jump in image quality. So for example, and also a jump in the size of images that you can feasibly model with current hardware. So the reordering also has a kind of practical aspect. So if we look at these generated faces from Celeb A, they're not at the level of GAN generated faces, but they're getting to be pretty convincing, right? I mean, you can see that a few more iterations of this, and we might have, autoregressive, just purely log likelihood models generating images that we can't tell are not real. And on ImageNet, ImageNet is a harder database to generate from because it's much more general, but you can really see that there's a lot more global structure going on here. Like this is clearly a dog. in the middle at the top and so forth. And even video, you can apply like this fully autoregressive approach to. Typically, you're going to be looking at the moment, relatively low resolution videos because it's pretty hard to model that much data. And okay, so going back a bit in time, an autoregressive model that's quite nostalgic for me was my own handwriting synthesis network, where the network was trained to generate people's handwriting one step at a time. And what's kind of interesting about that is going back to this debate about continuous versus discrete, this really was a fully continuous model. Things weren't discretized. Rather, there was a mixture density model at each time step that predicted the two-dimensional density, like the xy coordinate of the next, where the next point would appear in the sequence. So this data is recorded as a series of xy coordinates, xy points, as someone is writing with a pen. And this thing shows what the density map looks like, and you can see that it's very rich. There's a lot of structure there. There's a lot of covariance. It's not just sort of dropping finding the mean of the next thing. It's really shaping the predictions. And this bit at the bottom shows how it switches between different weights in the component as it predicts them. Okay, so moving on, I mean, that's all very well. What we've talked about so far is just like these autoregressive models at least give us a fighting chance of actually modeling unsupervised data in a reasonably coherent way. But ultimately, it's not about modeling the data, it's about, in some sense, representing the data. That's what we really care about. If what we care about is using unsupervised learning to generalize the new tasks, it's representations that we really care about. And so the way I think about representation learning is as a language. Deep networks, the way they work is that they learn complex and often hierarchical representations of the input data. So each layer kind of re-represents the layer below. And the way I think about this is a kind of internal language that the network is using to describe the data. And this is what I think is really key here. There's a sort of description going on here. And this means that you can get a kind of functional language emerging from a relatively simple task like object recognition. So if you have to recognize cats, then you might have a language that does something like identify pointy ears and whiskers and a tail. And if you put all those together, then maybe you can say this is a cat. And I think this is really interesting because it relates back to Wittgenstein's kind of ideas about language games that he put forward in his philosophical investigations, and a long time ago, when was this, 1930, something like that, where he talked about language. What he was kind of getting at was how can we have a language without defining a vocabulary? How do you get a language that emerges before there is a language with which to express it? And what he kind of talked about was just a language game being played between two people for some functional purpose. So his example he had was two builders, and they're collaborating on constructing a building. They're going to learn a language of bricks and blocks, and pass me this beam and put that block down there, because that's the language they need in order to carry out their task. And so some of you may have seen these papers on Distill by Christopher Olah and others. If you haven't, I really recommend looking. They're quite beautiful, and they do this amazingly detailed analysis of what is actually going on inside one of these great big convolutional networks that can classify ImageNet or similar data sets. And they find this kind of visual vocabulary is built up inside the network that starts at the bottom with really low-level things like edges and orientations, then builds up to what look more like textures, patterns, and then these composite things like eyes, bookshelves, text, rivets, birds, builds them up even further into complete objects, houses, dogs, wheels, so forth. And so, I mean, one thing to take from that is actually, even though supervised learning is very limited in the number of bits we're feeding into the system, it's learning something very rich from that, right? It's learning quite a sophisticated representation. So then the question is, well, do we expect unsupervised representations to do better than that? And the answer has to be yes, we do hope they would be. So ultimately, you can get a lot out of just image recognition, but of course it's always limited by the requirements of the task. So there's no need, if all you ever have to do is recognize objects, you probably don't need to internalize the laws of physics, for example. You don't need to learn all that much about the world, you just need to learn whatever it is that will help you to solve a specific problem. And the sort of guiding principle, I guess, behind unsupervised representation learning is that the representations should be more general, right? Anything that helps you to model or predict something about the world should be worth representing in your unsupervised system, and that should help you generalize. That's the theory. And so, as I said, what we really want is a neural network that describes data to us. So you think about these, image captioning experiments where people took images and automatically trained them to map from an image to a caption, like a man is standing on a train platform or something like that. We kind of want the network to be able to do that for us for a wide range of data. And we want to get these descriptions out of the network in some sense, or at least, oh, really? Sorry, I've taken a lot longer than I thought. I'm going to have to cut my presentation a little bit short here. Maybe we'll run over a little bit into the question time. Okay, so we want to get these descriptions out. How can we do that? One way that's been explored in the past is an autoencoder. So we encode the data, we put it into some compressed latent representation, and then we decode. And the idea is that the act of kind of squeezing this latent representation will enforce usable and kind of accessible representations that you can reuse elsewhere. Now, a sort of generalization of that is to, instead of just compressing this bottleneck, for example, by making it smaller using fewer hidden units, you can take a sort of information theoretic approach and look at what the coding cost is of representing the latent information. And I think that's unfortunate. I'm going to have to skip through a lot of this. Maybe I can give you just a little taster here of some of the so associative compression networks are a type of network that I've been working on recently, and they're a way of kind of escaping from a well-known problem with variational autoencoders, which is that the codes, when you make the decoders powerful, the codes tend to get ignored. The decoder just tends to take over. And associative compression networks get away from that by allowing the priors for the codes to be conditioned on similar codes, on things that are nearby in latent space. So you get this kind of natural clustering in latent space of similar codes. And the high-level idea behind this is that instead of learning individual data points, what you're doing here is you're learning the entire data set. You're looking holistically at the structure of the data set and saying, how can I represent what's in there? And so this idea is that the high-level information that you get out should organize the low-level data rather than just individually annotating it. And you'll have to look at the paper for the details. But if we look, say, at this set of reconstructions given by an associative compression network, so obviously the quality here again is not so high, but that's mostly a function of the decoder and of the fact that we went down to sort of very small images just for computational purposes, 32 by 32. But the point here was about the representations and not about the image quality. So what's going on here? Well, if you look, let's say these images on the leftmost column are the originals, the real images, and then the ones to the right of that are the ones regenerated from that image. So let's say look at this second one from the top. You could say, well, what's in the latent representation here? What it seems is that the network has described, so as I said, we want this kind of caption or description of the image, and the caption here could be a dark-haired man with stubble is looking straight at the camera and smiling on a light-colored background. And then it's handed that description off to the decoder and said, okay, now create a bunch of images matching that description. And it's more or less done that. I mean, they're not perfect, but it's generally capturing, they all look male, they're generally smiling, the pose is kind of straight on and so forth. So it's clearly capturing these high-level properties of the data that we wanted to capture. And you can see this also from the reconstructions. And actually, you can also see it from classification results. So this is, an ongoing thing with representation learning is how do you evaluate how good your representations are? And often what you do is you look at some sort of downstream task. If we took this representation, fed it to a simple classifier, could it tell us, for example, which MNIST digit we're looking at? And the answer is yes, it can. Okay, so I'm going to have to skip a lot of stuff here. Oh, one thing I'd like to say is that mutual information is a really vital concept when it comes to representation learning. As I've said, we want codes that describe the data well. And mathematically speaking, what that means is we want to maximize the mutual information between the code and the data. And so an autoencoder, a variational autoencoder, or these associative compression networks, they all actually do this implicitly, because the difference between decoding the data using a sample from the latent space, a latent code, and optimally, like the best possible decoding you could do without that latent sample, is a lower bound on the mutual information, which means that all the time you're minimizing the reconstruction cost, you're pushing up this lower bound on the mutual information. But it seems like kind of a sledgehammer approach, right? Like, if all we want is the codes, then doing all this work to decode seems very expensive. All we're trying to do is maximize mutual information. And are there other ways to do this? And there's a recent paper, Representation Learning with Contrasted Predictive Coding, has a very clever way of doing this. So instead of, in this situation here, you got some audio signal, a code C for some part of the signal, rather than doing what an autoencoder would do and attempting to decode. And so I should say, unlike an autoencoder here, this system is predictive. So rather than passing through a bottleneck and reconstructing the same data, it's taking codes and using them to predict future data. But rather than doing this prediction by exactly reconstruction, it attempts to find two codes and maximize the mutual information between them in a more direct way. And okay, I won't go through the details, there's not time, but it basically uses this idea of noise contrastive estimation, which is, given this code C and this code Z, take a whole bunch of other codes that could have been Z instead. And in practice, what you do is you have a big mini batch over training examples, and you take the Zs from the other elements of the batch, like the things that were not correlated with C, but rather came from some other audio sequence. And you say, how well can you distinguish this next code from the previous ones? Can you predict what it is against this background of negative examples? And this, you have to take it on faith here, but this kind of gives you another bound on mutual information and pushes up this descriptiveness of the codes about the data. And crucially, the further ahead you predict and the larger window you predict with these contrastive predictions, the slower varying, the higher level features you're looking at. You're going from maybe something low level like phonemes to something higher level like words or prosody or something like that. And the results are very good in practice. You get really quite incredible results for things like, considering that this is completely unsupervised and then there's just a linear classifier dropped on top afterwards, and you're getting classification rates that aren't that far off a fully supervised approach. And likewise, when you do an ImageNet, it's doing better than all of the other unsupervised approaches, at least that were out there at this point. So now, and how much time have I got left? So okay, this is going to have to be a real whirlwind tour. Unfortunately, I should have left more time to talk about unsupervised reinforcement learning. Simplest way you can sort of leverage unsupervised learning for reinforcement learning is to treat what's called like an auxiliary task. So basically you have a single network that's both maximizing reward and minimizing some unsupervised loss. And it's crucial that it's the same network, because basically what's going on here is that the unsupervised loss is going to affect the representations formed inside that network, and those representations should help it perform whatever reinforcement learning task it has to do. So this is really like a direct expression of this idea of learning structure and representing it makes you better at generalizing. And yeah, I'm going to have to just skip through highlights here, but in practice this really works, and it's becoming. This is actually, in the space of maybe a couple of years, this has now become quite a standard technique for modern RL agents, is to add these kinds of auxiliary losses. And here we show like improvements on performance on some RL tasks when you add. Well, first of all, they looked at input reconstruction, which is a very straightforward, just kind of model all the pixels, and then they looked at some other, auxiliary losses that were more efficient and really improved the baselines here. Okay, so skipping on, a more fundamental way of combining unsupervised learning with reinforcement learning, though, is to say that the unsupervised learning can actually guide the policy. So it's not just about shaping representations, it guides the policy. And at that point, what you have is an intrinsically motivated agent. The agent is just motivated by what it sees in the environment, what it can find out about the environment, or what it can control in the environment without having an extrinsic reward. And as with the rest of unsupervised learning, there's lots and lots of ways of doing this, and there's no consensus as to which one is right. Just to very quickly go through, there's two main strands. One of them is to reward the agent for being curious by guiding it towards novel observations from which it can rapidly learn. And there's lots of different ways that can do that. There was a paper, Curiosity-Driven Exploration by Self-Supervised Prediction, that came out last year. It's had a big impact here, which just looks at making predictions in latent space and looking for places where you find things that give you unpredictable latent values. And so that's a way of drawing you towards the stuff you don't know and away from the stuff you do know. There's lots of other ways of defining curiosity. Jürgen Schmid-Huber, who may or may not be in the audience here, has defined perhaps the sort of the most curious agent possible And I've given it the wrong title here, sorry about that, Jürgen. It should not say complexity gain there, it should rather say compression progress. And the idea there is you're seeking out data that doesn't just help you to learn about that data, but helps you to learn about everything you've ever observed. So if you had like a complete record of your past, in other words, a memory, then what you're saying is, how much did this new observation teach me about all of this stuff that I'd ever learned in my whole lifetime? So it's obviously quite an ambitious thing to actually work with, but I think it has a very interesting sort of property that's missing from these other curiosity signals, in that it's kind of retrospective. It tells you that you want to learn things to inform you about your past. And this last slide now is, as well as curiosity, another sort of information theoretic strand of unsupervised reinforcement learning, of intrinsic motivation, is what's known as empowerment. And here it's, again, mutual information kind of returns here. You're maximizing the mutual information between the agent's actions, in some sense the consequence of his actions. So for example, the state that those actions will lead to. And what this really means is that the agent wants control. It wants to be in a position where it is able to manipulate and accurately control the environment as much as possible. If you think about it in information terms, it wants the environment to be this clear channel, this noiseless channel that will exactly reflect whatever it was that their intention was to operate on that environment. And Daniel Polanyi, who was one of the authors of the original empowerment paper, characterized it as saying that a curious agent is like this eager young student who wants to learn everything at once. An empowered agent is like a wise old man who sits on a hill and just surveys everything but doesn't feel the need to move, as long as he's in this position where he can see everything and know what's going to happen. Okay, so what are the conclusions here? Well, obviously unsupervised learning gives us a lot more data to look at, but it's not clear how we should do that, right? There's no consensus on what the right objective is. Density modeling is one option. Autoregressive models are one option for density modeling. I'm not trying to claim that these are the only options by any means. What's clear, though, is that these unsupervised methods can yield very useful latent representations. The representations can directly benefit, for example, reinforcement learning, and we can also, as well as using them as a sort of auxiliary loss for reinforcement learning, we can also use intrinsic motivation signals to guide the agent's behavior. And that's the end of my part for now. Thank you.
So we have time for 2 questions. If you have questions, please go to the microphone standing in the back. Is there anyone I see next to the standing microphone? No questions? If there's no more question, we're going to have another Q&A section at the end of the tutorial. So we're going to take 5-minute break, and then please come back by 11.
I think we need to sit down now, guys.
Hello. Welcome to the second part of the tutorial on supervised learning. My name is Marco Aurelio Renzato. I am a research scientist at the Facebook AI Research Lab. In the first part of the tutorial, Alex introduced unsupervised learning in terms of compression and autoregressive models. In the second part, I will complement this view by surveying various applications of unsupervised learning, which are based on other frameworks and principles. So I will start by reviewing advances in unsupervised feature learning, then briefly mention methods to generate samples, and then conclude with methods to learn to translate between 2 different domains in an unsupervised way. And then the last few minutes will be about perspectives and a discussion about the challenges that are ahead of us. So let me start with a disclaimer. I will not mention all the works that are relevant, but I will just highlight a few representative works. And so let's start with the topic about learning, unsupervised feature learning in the continuous case. So let's say that this is your data, and this is already something a little bit misleading because oftentimes your data lives in a very high dimensional space, but still I think it is very important that whenever you get some data, you look at the data, right? And so doing a little bit of statistical analysis, look at what is the intrinsic dimensionality if you do PCA is something pretty important. But generally speaking, the goal of unsupervised feature learning is to associate a feature vector to any input data point. And this feature vector can have real values, can have discrete values, But the point is that from this representation, you want to be able to solve a variety of different tasks that are unknown when you learn the representation. In practice, you need to know that you always need to take into account very strong baselines. And PCA k-means are still pretty strong baselines if the dimensionality of the data is not too large. And in practice, even if you work with, let's say, high resolution images, applying PCA or k-means on image patches is oftentimes something that gives you a strong baselines for learning representations. So talking about learning representations in the continuous space, I'm going to refer to works in the computer vision literature. So I will do a brief historical overview and then talk about approaches that fall within the umbrella of self-supervised learning, and also talk about other approaches that are not based on self-supervised learning. So I would say that the bedrock of unsupervised feature learning dates back to PCA, right, early 20th century. And if you apply PCA on small image patches, you get essentially a DCT basis, which were published in the mid-70s and which led around mid-90s, late 90s to the JPEG format. In the applied math community, there has also been a lot of work about coming up with representations of images, again, dating back to early 20th century with the work by Haar, you know, the Haar wavelet, and then that went all the way throughout the century. Early 80s, we have the wavelet decomposition as we know it today. In machine learning, I would say that the breakthrough came with in 1986 with the publication of the paper by Rumeler, Hinton, and Williams about backpropagation as a way to train neural networks. And so there was a lot of excitement about training autoencoders. I would say that that went on until early 90s, and then at that point people switched to linear systems that were more easy to understand and to train. And most of the work in the computer vision literature went on designing feature descriptors like the SIP in the early 90s that had a lot of applications in the early 2000s. And it's not that people haven't worked on feature learning at the time. There is the seminal work by Bruno Salzen in the mid-90s about on sparse coding, for instance. But most of the computer vision literature was about hand engineered features, right? And so that changed around 2006 when Jeff Hinton and collaborators published a paper about training very deep, very hierarchical systems using autoencoders. So you would train these hierarchical models in a layered weight spatial using autoencoders, a variety of different autoencoders, from probabilistic autoencoders, sparse autoencoders, noise autoencoders. And there was a lot of excitement at that time, but then in 2012, Alex Krzyzewski and collaborators showed that you can actually train very deep convolution neural network in a supervised way. And so essentially, you don't quite need, so the conclusion at the time was that you don't quite need unsupervised learning. You can just use very large label data sets and get very good features. But then more recently, in the computer vision community, people realized that, okay, in computer vision, we have very large label data sets, but labels are never enough. And so now, in the past few years, there has been a lot of excitement about what they call self-supervised learning. And so that's what I'm going to describe next. And everything that I say is based on an architecture that is the convolution neural network, which I'm not going to review. I assume that you're familiar with it. You can see there are some good references that give a gentle introduction, and also a link to a tutorial that I gave at the summer school last year that is pretty introductory on the topic. So when you do unsupervised learning, very much like Alex described, you typically want to model the density of the input. You want to kind of reconstruct every input pixel, right? In self-supervised learning, the idea is that you use domain expertise to define a conditional task. So you define a subset of the input variables, which you use to condition. You try to predict the remaining ones. And so just that reduces the dimensionality of the prediction task. And the second thing is that you want to pick this subset of variables in such a way that the model has to learn the semantics of images. And oftentimes, you turn the original regression problem into a classification task that is easier to train. So let me give you a few examples of this. So in this work by Kardorsh et al., they take two image patches from the same image, all right? And then they try to predict the spatial relationship between these two image patches. And so in this case, they define a 3x3 grid. Given these two image patches, you need to predict that the second patch comes from the third position in this grid, okay? And the model is very simple. So you have a convolution neural network here that is used to extract features from both image patches. And then these features are fed to a classifier that has to predict, in this case, one of the 9 labels, one of the positions in the grid. So it is trained by cross entropy. And if you look at what the network learns after this procedure, you find that if you take a image patch like this, and you look at the nearest neighboring feature space, you find image patches that exhibit the same pattern. You know, leg things, or furry animals, or faces, and so on and so forth. And so then they tested on the Pascal VOC dataset, and they found that this method works much better than if you were to initialize the network at random, although not as good as if you were to use the large label dataset ImageNet. Okay? As a disclaimer, more recently, a few weeks ago, there has been a paper showing that actually, if you change a little bit the architecture, in this case, in particular, how you normalize the activations within the CNN, you actually can train things from random and do as well as ImageNet retraining. So everything that I say has to be taken with a grain of salt because the field is evolving very quickly, and things can change. But there are other self-supervised learning methods that have been applied to static images. But and here you'll find a couple of references. But the overall idea is to use domain expertise, domain knowledge, to define an auxiliary task that requires some semantic understanding. And oftentimes, you turn the task of predicting pixel values in a classification task that is much easier to handle. All right? Let's see another example of self-supervised learning applied to videos. In this work by Wei et al., they show to the network video snippets, and they need to predict whether, interesting. Well, this doesn't quite work, the video, but it's okay. So they need to predict whether the video snippet is played forward or backward in time, okay? And in order to do this, the network has to understand things like gravity. So here you would see a drop of water falling or going upwards, right? You need to understand gravity. You need to understand causality, friction, entropy, right? And so the way that they train this network is very much similar to the network that we saw before, where they divide the video snippet into chunks. Every chunk is fed to the network in terms of RGB values and optical flow. You go through a CNN that extract features, and then you give these features to a classifier, to a binary classifier, essentially. Okay? And you train everything by backprop. And if you use these weights to initialize a CNN for action recognition on this UCF101 dataset, you find that this initialization works even better than if you were to use a network trained on ImageNet with supervision. There are several other approaches for self-supervised learning from videos in general, like predicting one modality from the other, predicting how input frames have been shuffled. But I hope that you got the overall idea. There are other approaches to learn representations of images that are not based on self-supervised learning. And here I want to just show you another example. So here, the idea is based on the following intuition that a CNN has a lot of good inductive biases that really match the statistics of natural images and sounds. Right? Moreover, because a convolutional neural net uses small filters, if you do a Fourier analysis of a small kernel, you find that there is orientation and frequency selectivity. Okay? And so if you put together these two findings, you find that even a randomly initialized CNN extracts non-trivial features. Okay? And so in this work by Caron et al., they do something super simple and super effective. So the first step, for every image, they extract the features using the current parameters of the CNN. Initially, they are set at random. And then they run k-means in feature space. So now for every image, you associate a cluster ID. And then in the second step, they train the parameters of the model to predict from the image the cluster assignment. And now when you do that, you refine the features, and then you can go back to the previous step and re-extract the features and rerun k-means. Okay? And so if you just be careful about a couple of things, like making sure that clusters don't collapse. And so in that case, you need to reassign images to clusters. And if you make sure to equalize the prior distribution of clusters during training, then this method works really well. And for the ImageNet classification task, you get the performance that is here with the red bar, which is much better than if you pre-train using self-supervised learning approaches, like the green one is the one that I described earlier on, where you predict a spatial relationship between image patches. Again, it's still pretty far from supervised learning, but it's a remarkable progress towards that. And so to conclude this part, there has been a lot of progress on learning representations in a supervised manner for representing images. In particular, there is a lot of excitement about using self-supervised learning approaches where you use some domain knowledge to define a task, an auxiliary task that requires some semantic understanding, and for which you try to remove the original kind of regression task and you move to a classification task. And the only thing that you need to make sure is that the network doesn't cheat, that it doesn't collapse features or it doesn't exploit biases in the data set to perform the task that you want. And so there are some subtleties here, and these are very much method dependent. So let me now go on unsupervised feature learning for text as an example of working in the discrete space. So here, there is a fundamental difference between images and text in the sense that the atomic unit in text is a word, which is a discrete token, right? While in images, typically pixel values are treated as a real value object. And while a word carries a lot of information, a pixel value carries almost no information at all. And so because images are continuous, search is typically easy. You can do gradient descent, but in text, you need to, it's a combinatorial problem. So you need to have you need to use some heuristics. At the same time, because images are discrete, modeling is typically a little easier because you use a multinomial distribution. And so if you want to model uncertainty, you have it right there. While for images, modeling, if you stay in the continuous space, is a little harder. And so let me start again by a brief historical overview. Since text is symbolic in nature, I would date back everything to George Boole and his contribution to logic reasoning, right? And the use of treating text in terms of symbols has had a long influence. If you think about a Turing machine, what you write on the tape is a symbol, right? And so it was not until the 50s that people consider associating to symbols distributed representations, right? But at that time, they didn't quite know how to train them. And so they were considering only linear single-layer methods like the perceptron, and that had clear limitations that were highlighted in the paper by Paper-Minsky. And so it was really until the introduction of backpropagation in the mid-80s that people were able to actually train effectively neural nets. And if you look at Jeffington's papers from 1986, you already find the notion of associating towards word embedding, so a distributed representation. And so I would say that if you look at LSA, which also came in the late 80s, there you build a Word document count matrix where documents could be sentences, and you apply a PCA on that matrix. And that PCA decomposition already gives you word embeddings, right? And so, again, the bedrock of what we do is really PCA, again, very much like we saw in Vision. And if you think about, if you fast forward and you go to 2013 Word2Vec, Word2Vec is essentially an online version of LSA where you replace the mean square error loss with cross entropy, right? So these things are intimately related. Going back to the 80s, there was a lot of excitement. Again, then we went through a winter session in which people were mostly considering count-based representations. In the early 2000s, there was a lot of excitement on topic modeling. So a way to associate kind of discrete representations at the document level. And the major contribution by Tomasz Mikolov in 2013 was to make available a toolbox to learn word embeddings, and showing that this could be learned very efficiently, and it's a pretty general purpose thing, as we shall see later. And since then, there has been a lot of interest in the NLP community to represent not only words, but also sentences, and I'm going to describe the latest contribution towards that. So let me briefly summarize Word2Vec. So here the idea is that the meaning of a word is determined by the context. So if I hide a word here, probably by reading the sentence, you can figure out what the missing word is. So the context really determines the meaning of that word. Not only, semantically similar words often share the same context. And so Word2Vec leverages these insights and associates to every word a continuous representation, a vector in RD. So for every word in the dictionary, you have a vector in RD, and initially these things are initialized at random. And then what you do, you take a small window of text, okay, let's say 7 words, you take the word in the middle, you fetch the corresponding word embedding, represented by this rectangle, and then you project this word embedding into via a matrix through a distribution over words in the dictionary, and you try to predict the words in the context. Okay? And you train this by cross-entropy loss, and so it's a simple linear model that is factorized, that is trained via backprop. And what you find is that word embeddings of similar words end up being nearest neighbor, and the embedding space has nice geometric properties. For instance, if you take the word embedding of kings and you subtract the word embedding of king, you get a vector that represents number. And so if you add that vector to the word embedding of queen, you find a vector that is nearest neighbor to the word queens. And the same is true for gender and for other properties. And so the beauty of Word2Vec is that it's its simplicity and its generality. So you can apply the same ideas also to graphs, right? So you can say a node in a graph is represented by its neighbors. And so I can learn an embedding of each node in the graph by predicting who the neighbors are, right? And again, the idea is to predict a word from the context, right? So now the question is, how can we extend this to represent sentences? Obviously, we cannot enumerate all possible sentences. The space is combinatorial. They're way too much. We need to leverage some compositionality that is in language. And so I'm going to present the latest advancement in the field. This is called BERT by Devlin et al. And so here they take 2 sentences, okay? And here you have a special token that says, I'm going to start my sentence here, and you have another special token that says this is the separation between the 2 sentences, okay? And then for every token, you have like a deep net. So you have a lot of computational blocks that form a deep net. And each computational block takes as input from all the blocks at the layer below. Now, because we want to work with sentences, we don't want to restrict the length to be a certain length, right? We want to work with variable length objects. And so one way to do this is to use attention. And here I'm going to give a brief high-level idea of how attention works. So for every block, let's say we are looking at the word set at a given layer of this architecture. For this block, you have a representation. Let's call it hj, okay? And each block has a certain representation. What you do a dot product between the representation of this block and the representation of all the blocks of the words in the context. So now you're going to get, when you do the dot product between two vectors, you get a scalar. And then you turn a step 3 here, you turn these scalars into a probability distribution, so numbers that are positive and sum to 1 by going through a softmax. And then at step 4, you compute the representation for the layer above as a weighted sum of the representations of each block with weights that come from the output of the softmax at step 3. Okay? In practice, this attention-based mechanism that is called transformer by Vasvani et al. Is a little bit more involved because you have different representations for computing this dot product and for computing this weighted sum, and you have multiple of these things at each layer, but the overall idea is what I just described. And so the idea is that eventually you get a representation that depends on all the words on the context, and it is independent of the length. And you do this at every layer, and now let's see how this is trained. So the way it is trained is that there is with a certain probability, with a small probability, you hide a word, and you try to predict that word at the output, okay? Then they have another, so again, this is an example of a denoising autoencoding task. And then with some other probability, you take a word, you replace that word with a random word, and you try to predict at the output the original word that was in that slot. Another task is to predict the actual original word, and yet another task is to say at the output of the very first token, that beginning of sentence, you try to predict whether the second sentence is a sentence taken at random from the training set, or whether it is the genuine next sentence that follows the first sentence. So now you need to have some way to understand sentences and to represent sentences to perform this task. The authors evaluate this model on the GLUE benchmark that consists of 11 different tasks from classification, from entailment, and so on and so forth, and they found that this method works much better than other alternatives to learn sentence representations, and much better than word-to-back. So you can see this method as a deep version of word-to-back in the end, right? And this works even better than supervised approaches because on these data sets, typically you don't have a lot of labeled data. And so this is an example where unsupervised learning really shines. And so the conclusion of this is that we have very good tools to represent sentences, and now also we have pretty good tools to represent, we have very good tools to represent words, and now also sentences, and this works in practice in lots of different applications. Let's switch gear, and let me talk briefly about another application of unsupervised learning. Now, the task is to generate samples that look like training data. And so here the idea is that you have a random number generator, and you want to turn these random numbers in data points that look like your training set. And so this could be useful for learning representations, pretty much like Alex said. If you can recreate the data, most likely you have understood the underlying properties of that data. It could be useful for planning. So if I want to decide what to do next, I can simulate in my head what future scenarios may look like. Or it could just be used for fun, because generating images is fun. And so right now there is a lot of excitement about generative adversarial networks to generate images. Here are some examples. Here are some examples where the generation is conditional on a class label, and it's really remarkable. It is, it blows me away. Overall, if you consider what we could do 5-10 years ago. There are also other approaches, like autoregressive approaches, like Alex showed before, approaches based on latent variables, and so forth. And it seems to me that the crucial part is actually the architecture that you use, the specific convolution neural network that you use more than the loss function, really. And there are a lot of challenges. So I would say the major challenge is how to evaluate these generative models. Another challenge is how do you model high-dimensional distributions and how do you model uncertainty? Because if you have to predict a lot of variables, then there are many plausible things that you can possibly generate. And that goes back to how do you measure quality of the generation. In NLP, there are also a lot of methods to generate text. As Alex mentioned, there is a lot of work on autoregressive models, like RNNs that generate text. There are also other approaches that are a little older that are based on retrieval. So here the idea is that you have a fixed set of candidates, and when you want to generate, you rank these candidates, and then you copy and paste the highest ranking candidate. More recently, there has been also work that tries to combine these two approaches. So the idea is that you first retrieve, okay, and then once you retrieve, you edit using a parametric model. Okay? And here you have a few pointers for works along these lines, and there are actually many more. And again, the challenge is to generate long pieces of text that are coherent. We are pretty good at generating short sentences, much less but there is a lot of room for improvement for generating a document, right? It's very difficult to generate things that are coherent, that stay on topic. And again, a major issue is how do you evaluate these generative models? Right? How do you automatically assess goodness of the generation? Let me conclude as last application of unsupervised learning, talking about methods to translate between two different domains. So here the idea is that you have a bunch of points in domain 1, a bunch of data in domain 2, and you want to learn a mapping that brings a data point from domain 1 to a data point in domain 2. This could be useful for a variety of applications. In general, it is a useful skill that an AI agent should have, because if you want to quickly adapt to a new environment, you need to be able to make analogies to say, oh, this situation is similar to something that I learned before, and I can reuse my skills for that. In computer vision, there is a seminal work by Zhu et al. That is called CycleGAN. So here is an example where you have a bunch of photographic images for domain 1, and let's say a bunch of Monet paintings for domain 2. And the task is to say, given a Monet painting, how can I fantasize what the corresponding photographic image, what Monet saw when he was painting, right? And vice versa. And in the paper, they give also other examples, like turning zebras into horses, turning summer images into winter images, and so on and so forth. So let's see how this works. So you take an image from domain 1, let's call it X, and you have two generators. So you have a generator that maps an image from domain 1 to domain 2. That's the blue box. And you have a generator that maps an image from domain 2 to domain 1. And that's the red box. No. So now, you take your data point from the first domain. You apply the generator that takes you to domain 2. And that gives you this y hat. Now, the data set doesn't come with what is the ground truth y hat, right? We are in the unsupervised setting. So what you do, you feed that as input to the other generator that takes you back to domain 1. And now you have the x hat reconstruction, which you can compare to the original x. And that's what they call cycle consistency. So this is like an autoencoding task where the later representation is actually a point in the other domain. And you do the same for images belonging to domain 2. That's what you see at the bottom here. Now, so far so good, but this doesn't do what you want necessarily, because when you produce this data point, there is no constraint that this data point actually belongs to the domain that you want, right? And so you need to have another constraint. And the constraint that they have is an adversarial term in the loss function. So they train a classifier to predict whether the input comes from the output of the generator or is actually a genuine sample from domain 2. And when they train the generator, they try to fool this classifier as much as possible. by essentially trying to increase its loss. That's it. So it turns out that this is a pretty general principle that can be applied also to text. And there are a lot of applications in text that could benefit from this idea. And here I'm going to talk about some recent work that my collaborators and I did for machine translation. So here the idea is that you have a lot of raw text in 2 different languages, but you don't have any translation. You don't have a collection of sentences in one language with a corresponding translation. You don't have that. You just have text in each language, and this text doesn't correspond to each other. And what you want at the end is to learn to translate. So this could be useful because for the vast majority of language pairs in the world, we actually don't have parallel data. So we don't have a collection of sentences with a corresponding translation. But we do have raw text in each language, right? So before I explain how one way to do unsupervised machine translation, let me introduce the idea of learning to translate words, which is a preliminary steps towards translating sentences. And so here the idea is that the context of a word is often the same across languages, because even if we live in different parts of the world, we share the physical, even if we live in different places, we share the same physical world. So the relationship of, let's say, cat and kitty is the same in Italian and Japanese, and these are 2 words that are pretty close, but if I look at cat and car, those are pretty far. And this is true in all the languages. And so here the idea, let's see if this animation works, great. So here the idea is that, let's say that you want to align 3 languages, okay? You first learn word embeddings in each language separately, okay? So let's say you do word2vec in each language, so now each word in each language has associated an embedding, okay? And now the idea is that because the relationship between words are the same across languages, a simple rotation suffices to align these word embeddings, okay? And so what we do adversarial training. So we have a classifier that is trained to distinguish whether the input comes from, let's say, a word embedding from language 1 or a rotated word embedding from language 2. Okay? And when we train the rotation matrix, we try to fool this classifier. And so this gives you a rough alignment. And so what you do at the end, given a word, you apply a rotation, then you look at the nearest neighbor word in the other language, and that's your word translation. And then if you read the paper, there are some refinement steps that I'm going to skip for the sake of simplicity. But what you find is that if you learn this rotation using ground truth word translations, 5,000 word translations, you do actually slightly worse than if you use this unsupervised approach on some language pairs. Because here you can learn, you can ground this rotation using many more anchor points. They are noisy, but you can use many more. And so actually when you try to infer this bilingual accent, you can do even better if you use the unsupervised approach. So this approach that is called Muse can be used as a stepping stone for doing translation at the sentence level. But you cannot just directly use this because, again, we don't quite know how to represent sentences. We cannot associate a single representation to each sentence, like a sentence embedding, a unique sentence embedding for sentences. We need to use something that is compositional. And so what we use is a sequence-to-sequence model where, let's say you take a sentence from the English data set, you encode it, you got a Latin representation. From this Latin representation, you decode it, and you get some translation in Italian, right? So you can imagine that this encoder and decoder is a recurrent neural net. It could be a transformer. It could be anything, right? But now we don't have the ground truth translation for any of the sentences in English. And so what we do, pretty much like in the second guide in Vision, we feed this to another sequence-to-sequence model that takes this sentence and extracts a Latin representation from there, reconstructs the original sentence in English. And now we have a way to compute reconstruction error between this y and this y double hat. But now, like in the cyclogram, we need to add another constraint to make sure that this intermediate sentence is a valid, in this case, Italian sentence. So in the cyclogram, they had adversarial training in this space, but now it is a little difficult to do this in machine translation because we have a discrete sequence of tokens, right? And so we don't quite know how to backpropagate in a very efficient way. And so instead of doing that, we do denoising autoencoding to make sure that the decoder produces fluent sentences, okay? So you take your input sentence, you add noise, and here by noise I mean you drop words, you swap words, and you force your decoder to reconstruct the original clean sentence. So now when the decoder is used, it's going to produce always fluent sentences because it has learned regularities in the data. The last caveat is that if you just do this, it won't work very well because there is a chance that the decoder cheats in the sense that it may reconstruct well when you feed sentences in the same language, so when you do autoencoding, but it may not reconstruct well when you do translation. So you need to make sure that the representation produced by the encoder is the same both when you do translation and when you do language modeling. Because if you use two different parts of the latent space, then this is not going to work. And so there are several ways to do that. If the two languages are related, what we do, we share all parameters in the encoder, and also we learn word embeddings jointly, and we break words into subwords. So there is a lot of overlap because we are going to have a lot of subwords that appear in both languages, like English and French, right? If the two languages are not related, then we apply the Muse algorithm that I described before to align the word embeddings, and we share all parameters in the encoder, and that guarantees that the latent representation is shared. And so if you apply this on a large data set for machine translation, you find that this approach works better than previous approaches on the same task. And keep in mind that before 2018, performance on these large benchmarks was essentially zero. We are pretty far from the supervised state of the art, but still, if you read these translations, you can actually, they are useful. You can read them, and they are pretty good. If you, just to give you an idea, the performance that we get using 10 million monolingual sentences in each language is about the same as using 100,000 parallel sentences, as if you were to train supervised with 100,000 parallel sentences on languages like English, French, English, German. It works also on more distant language pairs like Urdu. So here is an example of Urdu. If you have never seen it, it looks like Arabic, but the language is related to Hindi, actually. And so in this case, this is pretty interesting because there is actually parallel data in Urdu between English and Urdu, but it's like genome translation. It's like movie captions translation. So if you then want to, say, translate news, it doesn't work very well. But now if you take monolingual data, but if you scrape news websites, both in English and Urdu, and you use this unsupervised approach, you actually do better than if you were to use the parallel data set. Okay, so the overall idea here is that in order to align to domains, there are a few principles that apply pretty widely. So one is cycle consistency. So if you map to one domain, you need to be able to go back to the original domain. And the second one is to add constraints such that when you map to one domain, what you generate actually has the same characteristics of the domain that you want to have. Okay? Let me conclude with some discussion about what the challenges are ahead of us. So in my opinion, the first and the biggest challenge is really the definition of good metrics. So let's say, let's consider unsupervised feature learning. It would be very good to have consensus on a good set of downstream tasks and metrics to evaluate feature learning methods. In NLP, there has been quite a bit of work towards this goal, And we have benchmarks like Santival, like the glue benchmark that I described earlier. For generation, it's even trickier because there are many plausible ways to, to predict what the next sentence is going to be, right? And so, again, in NLP, there has been quite a bit of work towards this goal. So for specific applications like machine translation, which you can see as a conditional generation task, every year there is a competition. There are a bunch of different metrics that slice the evaluation in different ways, and there are very large benchmarks for comparing different models. In dialogue, there is a platform for evaluating dialogue systems. But for instance, in vision, I haven't seen the community getting together and getting to a level where there is consensus on how to evaluate model. And this is, I think, a big challenge, even more, I think it's a big roadblock, even more important than designing better models, because if we don't have a good set of tasks and metrics, it's really difficult to compare models and to assess whether we are making any progress, right? So the second challenge is generalizing our unsupervised learning algorithms. So for instance, in NLP, the methods that I described are based on prediction of a missing word from a sentence, right? But how about if I have a missing phrase, right? How about if I want to extract features from a sentence with any missing part? I would like to be able to do that. In vision, self-supervised learning shows a lot of promise, but again, every auxiliary task gives you a different slicing of the data. And so how many more tasks do we need to design to get a more holistic view of what the data is? As Alex mentioned before, autoregressive models also have limitations, right? Because you need to define an ordering, and depending on the application, the ordering may be pretty critical. And then you need to also account for efficiency. So when you generate, these models may be slow. And so I don't know what is the right answer, but let me describe a more general framework and see how, what are the pros and cons of this. So a more general framework is the energy-based model framework by Yann LeCun. And so this is a more general framework because essentially the only thing that you need to define is an energy function. So for every input data point, you want to be able to assign a scalar value. Okay? And this energy function is parameterized. And the goal of learning is to make sure that the energy is lower where there is high density of training data, okay? As you can see in this picture. So training is about shaping this energy function. And so why is this useful? Well, let's say that you have some missing variables, okay? Or let's say that you add noise to your input data point. In order to denoise, what you can do is you can run a search in your energy surface to find the closest minimum to your starting point, right? And because the energy function is parameterized by some deep neural net with deterministic or stochastic variables, you are able to extract features from any subset of the variables. But this comes with a catch. And the catch is that it's very hard to learn these energy functions. So because you only observe positive samples, if you want to learn these contrastive functions, you need to be able to fantasize negative samples. But if you work in a very high dimensional space, you need to push up the energy lots and lots of points, right? And this may be infeasible. And there are different ways to define negative samples by search, by sampling, using things like contrastive divergence. Because it's really hard to, because the space is too large to explicitly pull up the energy, you may want to consider other approaches, like if you use an autoencoder and your energy function is the reconstruction error. One way to constrain the model is to have a bottleneck. And so to say, well, if my code is low dimensional, or if it is sparse, if you inject noise, then I simply don't have enough codes to reconstruct well every input data point. And so if I don't have enough codes and I need to reconstruct well my training samples, then necessarily I'm going to do a worse job at noisy data, right? And so, well, my animations don't work, but you got the idea that if you like move this parabola and you put the minimum where there is high density of training data, necessarily elsewhere you have high density. Sorry, you have low probability, let's say. And so, but you see that there is a trade-off. So you want to model very well your data, and your data might be in a very high dimensional space, maybe very nonlinear, right? And so you want to have a very flexible model, but at the same time, you need to make this energy function contrastive. And so the pull-up becomes very, very hard. And so the question is, are there better ways to pull up this energy function? Are there more general frameworks that are more workable than this one? And to which extent can we design losses and frameworks in a way that is agnostic to the architecture and the application, right? Because the fact that I use a convolutional neural net gives me a lot of good biases and constrain my search space. The third challenge is about uncertainty. So whenever you make a prediction in a high dimensional space, oftentimes there are many plausible ways to, plausible future outcomes. And so, for instance, there are many ways to complete this sentence that are both plausible, right? And so there are many methods to deal with uncertainty. You can have latent variables, you can use GANs, and so on and so forth. And there is a question of which method gives you a better fit, and which method is more efficient. And so let me conclude with a final note. So our interest in unsupervised learning is because we want to learn with less supervision, right? As Alex said, we are not interested in doing well at a task, but we want to learn a skill, right? And so we want to learn more efficiently from less labeled data. And there are a lot of subfields in machine learning that share the same goal, right? Of learning with less data to be able to transfer knowledge. Here I mentioned just a few. And so perhaps one way to think about unsupervised learning is in a broader context, right? And so maybe one way to approach unsupervised learning is also by taking these other learning settings and gradually reduce supervision. And more generally, I think we should not look at unsupervised learning in isolation. And so if we go back to the nice metaphor by Yann LeCun, we shouldn't try to just, you shouldn't want to just eat the cherry or just eat the filling of the cake. You really want to take a whole slice, right? And so what I mean is that I can hardly imagine how we can get reinforcement learning to work well without leveraging the information that is present in the observations, right? At the same time, I can hardly imagine how we can do successful unsupervised learning by looking at that in isolation. So it has to be part of a bigger system, and if another component in your learning system receives a sparse reward, that may not be sufficient for training your parameters, but can inform you about what are good unsupervised tasks that you may want to consider. And so the conclusion is that unsupervised learning is really about learning with helping the agent or the model learn with less interactions with the teacher. And there are several applications. Some of them are already pretty successful. But in general, there are open questions. So one open question is about defining good metrics. Another big open question is about making our algorithms more general while retaining efficiency. And the third one is about integrating supervised learning in a broader context of your learning system. And with this one, I want to thank you, and we'll be happy to take your questions now. Thank you.
So there is time for about 2 questions, and then as I asked earlier, it would be nice if you could wait a bit until we have the question and answer without leaving the room. Obviously, people will do it. So do we have any questions from the audience? So there are 4 oh yeah, there you go. Yes, please.
There is a microphone.
Can you find the microphone that is standing somewhere and then ask a question? Okay. Yes, at the very back, while we are waiting for him to go to the microphone, yes. Are the microphones working?
So thank you for the tutorial.
there you go, okay.
Could you please comment how all these beautiful tools of unsupervised learning may be applicable for anomaly detection tasks, both in, say, images and videos?
So, okay, I guess I need to just do. So that's not, I would say, the mainstream task, but you can see unsupervised learning being really learning only from positive data, and so essentially doing density estimation and figuring out data points that are very far from what you have observed. And so I think I would say that in other communities, I would say that anomaly detection is the application of unsupervised learning. Although I would say in machine learning, that's not, I think the main drive is mostly about modeling data and learning representations for other tasks.
And I agree with that. I mean, I was just going to say, obviously, with anomaly detection as a supervised problem, the problem is, massively unbalanced data sets. Whereas I think, in some sense, you get it for free with unsupervised learning. If you have a good model of the data, then you can just see, how likely something is under that model, and anomaly detection should follow quite naturally, I guess, from a good unsupervised model.
Okay, so the next question at the very back, does the microphone work for you? No? Yeah.
Okay, one quick question. If I understood correctly, you mentioned in passing that architectures are sometimes more important in order to get good performance with GANs than how you train them and which loss function. Could you elaborate on that a little bit?
Oh, what I meant is that if you look at, so convolutional neural network gives you a strong, a very good starting point, right? So they are designed with very good inductive biases, and oftentimes, and nowadays you see that many approaches from autoregressive models, GANs, latent variable models are able to generate pretty realistic images, right? And so there seems to be enough evidence that more than the loss function, the choice of architecture is oftentimes more important for the quality of the generation. And so if you use a GAN with a weak convolutional neural network that, I don't know, doesn't have the latest normalization layer, then the generation are not quite as good. And you can get as good generation as GANs if you use also other approaches like, the autoregressive methods that Alex mentioned. Of course, there is the question of how do you evaluate different models, and right now for image generation there are quite a few metrics. I don't think they are particularly satisfying in my view, and so maybe it's also a question of defining good metrics to assess quality of these generating models.
And when you say architectures in this context, do you mean which type of architecture, or more
By
like
architecture,
how many layers, etc.?
By architecture, I mean the kind of generator that you use, the function that turns a sample from a Gaussian distribution to a data point. So what kind of parametric function do you use?
Cool, thank you.
Hello. Yeah, thanks for that great talk. I really liked your coverage of the representation learning within specific domains and the state of the science. Could you comment on the state of the science as we look across very different domains, for instance, images and text? Is there work happening in that field?
So yes, there is a lot of work on multimodal learning, so learning from audio and videos, text and images. In fact, there is a lot of excitement within the self-supervised learning approach about predicting one modality from the other. So yeah, no, that's definitely, sorry, I apologize. I think I had only one or two references about that, but there is a whole subfield that works along on that.
So just a quick follow-up. You think we could use like cyclogans and things like these for similar tasks?
Oh yeah,
as well?
absolutely,
Okay.
absolutely,
Okay.
absolutely.
Right,
Yeah,
thanks.
yeah,
Thank you.
totally. Yeah. Of course, then it really depends on the application, because for some application going, let's say you want to do unsupervised speech recognition, right? There are some challenges when you go from text to speech, right? Perhaps there is more ambiguity when you go in that direction than when you go from speech to text. And so I don't want to overly generalize, but I would say that in general there is a lot of work on that, and for some applications it is less obvious, but for others, yeah.
Thank you. Thanks.
I wanted to ask if there's any way we could get access to the presentation material.
Absolutely. So it's going to be on our websites by tomorrow. So we're going to upload a PDF sometime in the afternoon. Check on our websites. My website for sure. Alex, I don't know. Yeah.
That's a good question. Is there a...
In the worst case, I'll try to tweet it as much as I can so that you'll have access to the slides by tomorrow or so. Yes.
Cool.
But we'll try to put the link on the conference homepage as well. Yeah.
We'll definitely make them available.
Thank you.
Well, thanks for coming to the tutorial. That concludes the tutorial.